In this video, we take another look at the rank of a matrix in terms of the row space and column space, and we relate this rank with the dimension of the null space of the matrix. Recall that an n by n matrix A defines a subspace of Rn and of Rn. The subspace of Rn spanned by the columns of matrix A is called the column space of the matrix, while the subspace of Rn, which is spanned by the rows of the matrix, is called the row space. Suppose A and B are two n by n matrices. If A and B are row equivalent, then the row spaces of A and B are the same. Moreover, if A transpose and B transpose are row equivalent, which is equivalent to saying that A and B are column equivalent, then the column spaces of A and B are equal. Because the row space is a subspace of Rn, it has a finite dimension, and the dimension is what we call the row rank of the matrix. Similarly, the column space is a subspace of Rn, and its dimension is finite, and it will be called the column rank of the matrix. Note that if A and B are row equivalent matrices, such that matrix B is in reduced row echelon form, then the row rank of A is actually the number of non-zero rows in B. To illustrate, consider the matrix A as shown. So we compute the reduced row echelon form of the matrix. After performing these elementary row operations, we find that this matrix in reduced row echelon form is row equivalent to A. Now this matrix A has 3 non-zero rows. So from this we see that the row rank of matrix A is 3. So from our last computation, we have this row equivalence. Let's call this matrix in reduced row echelon form matrix B. By definition, the column space of matrix A is the subspace spanned by the columns A. Okay, so there are 5 columns, so we have 5 vectors in the spanning set. In matrix B, we see that columns 1, 2, and 4 are the columns that contain the leading one. This column, and this column. So we see that these 3 vectors, rather the vectors associated with these columns, form a spanning set for the column space, and those 3 vectors are this column, and this column. So that's what we see here. And in fact, from this RREF, we also see that these 3 matrices are linearly independent. So this set is linearly independent, and this implies that it is a basis. This set is a basis for the column space of A. So this tells us that the column rank of A is 3, because the column space has dimension 3. So we saw in the last illustration that the row rank of matrix A and the column rank of the matrix are both equal to 3. So they are equal, and that is not a coincidence. In general, for an m by n matrix A, the row and column ranks are always equal. And because of this equality, we make no more distinction and simply refer to both as the rank of A and write this notation. The notions of row and column spaces and rank have some applications to systems of linear equations. Suppose A is an m by n matrix. Recall that the solution set of the homogeneous linear system Ax equals the zero vector is a subspace of Rn, which we call the null space of matrix A. So because this is a subspace of Rn, it has finite dimension. And the dimension of the null space will be called the nullity of the matrix. Since the null space is a vector space, one thing of interest to us would be how to obtain a basis for this vector space. In this slide, we give an idea on how we can find a basis. So given an m by n matrix A, to find a basis for its solution space, we simply solve for x in the homogeneous linear system Ax equals 0 using Gauss-Jordan reduction. So because this is a homogeneous linear system, it is always consistent, and there are two possibilities in the solution set. Either it has a unique solution, or there are infinitely many solutions. If the solution is trivial, then the null space is equal to the zero vector space. And in this case, our convention is that the dimension is 0. Otherwise, when the system has infinitely many solutions, then the solution would involve several arbitrary constants. So these are the parameters in the solution set. In this case, every solution can be expressed as a linear combination of some vectors with the arbitrary constants acting as coefficients. If the vectors p sub j's are linearly independent, then they form a basis for the solution space, and the number of such vectors will be the nullity of A. That's the dimension of the null space. To illustrate, let's consider the linear system as shown. Let us find the solution space of the system and a basis for this solution space. We want to find the null space of the matrix of coefficients and a basis for that null space. The augmented matrix of this homogeneous linear system is as shown here, and by Gauss-Jordan reduction, we find that the augmented matrix is row equivalent to this matrix in reduced row echelon form, and from this we see that the system has infinitely many solutions, given by x1 equals 2x3, x2 equals negative 3x3 minus x4, and x3, x4 are parameters. Okay, because columns 3 and 4 do not contain a leading entry of any row, and so the vectors associated with these columns are free variables, and those Those are x3, x4. So every solution to this linear system can be expressed as a 4-vector, okay, where x3 and x4 are free variables, so they are arbitrary, while the first component is twice the third component, and the second component is -3 times the third component minus the fourth component. So essentially obtained from this description of the solution set. Now observe that this vector here can be expressed as a linear combination of two vectors. Okay, so essentially we just split this vector into a sum of two vectors because there are two free variables. So two vectors where the first vector involves only r1, the other vector involves only r2. So that will be the vector 2r1 minus 3r1, r1, 0, plus the vector 0, negative r2, 0, r2. And in the first vector, we can factor out r1, meaning the vector can be written as a scalar multiple of r1 with the vector 2, negative 3, 1, 0. And similarly, the second vector can be written as a scalar multiple of r2 with the vector 0, negative 1, 0, 1. So the null space is given by the set of all vectors of this form. In other words, it is the set of all linear combinations of vectors 2, negative 3, 1, 0 and 0, negative 1, 0, 1. So it is the subspace spanned by these two vectors. So we have here a spanning set for the null space. Now we can check that these vectors are linearly independent by observing that the matrix whose columns are these vectors is row equivalent to this matrix, and or where both columns contain a leading entry of some row. Okay, so these vectors are linearly independent. So the set B, which contains the two vectors 2, negative 3, 1, 0 and 0, negative 1, 0, 1 is a basis for the solution space. Therefore, the nullity of the matrix of coefficients A is equal to 2. In other words, the solution space of this linear system is a two-dimensional vector space. So we see that the nullity of matrix A is equal to the number of free variables in the solution set of our homogeneous linear system, which is equal to the number of columns in the RREF of matrix A that do not contain a leading entry of any row. In fact, that observation holds in general via the rank nullity theorem. So if A is an m by n matrix with n columns with r non-zero rows in its RREF, then the dimension of the null space is equal to n minus r. So we have this relation. The sum of the rank and nullity equals the number of columns of matrix A. So as we mentioned earlier, that's what happened in the last illustration. So for this 2 by 4 matrix, which is the matrix of coefficients of our linear system, we saw that the rank is 2. There are 2 non-zero rows, and there are 2 columns that do not contain any leading entry of any row. Okay, so the nullity is equal to 2, and the sum is equal to the number of columns.